All right, today we're going to take a look at the last section that we're doing in chapter 1, which is 111, and these are cubic models. And in particular, there's another part of this section where it's us having to make decisions about what model is appropriate to try. So we haven't had to do that yet. We've just been, for the most part, we've been given a question that just says, find the quadratic model, right? Or find the linear model. So when we get to your test next week, there will be one question where it gives you data and it says, find whatever is the most appropriate model. And we're going to talk about how to do that today too. So for starters, a cubic model, this is called cubic regression in your calculator, has the form f of x equals ax cubed plus bx squared plus cx plus d. A can't be 0. If a were 0, we'd have a quadratic equation or maybe a linear equation, depending. B, C, and D could be 0. At the very least, they're constants, they're numbers. And there are a couple of features that are really important for cubic models. The first one is that it changes concavity. So it goes from concave up to concave down, or concave down to concave up. The second one is something you may or may not see, and that's a behavior change. And by behavior, we always mean increasing, decreasing. That's the behavior. Is it increasing, is it decreasing, or is it constant? But that doesn't apply right now. So there's 4 basic pictures that you could get if you're dealing with a cubic model. These are the 2 that do not have any behavior change. Notice they still change concavity, right? My red dot right there marks that it's concave up after that point, concave down below. And it's reversed with that particular one, the second one. It's concave up before it and concave down after it. But they're solidly increasing on the first one, solidly decreasing on the second one. It doesn't change behavior. But it could. You could have a graph that does this or this. So there's the concavity change. I'm going to mark that again with the red dots. On the first of the 2 pictures I just drew there, I have it concave down, then concave up. The other one is concave up, then concave down. But we definitely see it change from decreasing to increasing or increasing to decreasing. So that's a feature of a cubic graph that we haven't had so far on any of our other graphs, where it actually changes the behavior. All right, so we're going to do an example. Grab your calculator if you would. I'll grab mine as well. We have a table, and in our table we have the number of births in specific years. These are to older women who are 45 years and older in the United States. Now, we've talked before about the fact that we don't want to put an actual year in the calculator. The harder that the model is, so linear model, you can kind of get away with it, but cubic models, logistic models that are harder for your calculator to make calculations from don't tolerate input values that are that big. So we typically want to align our data somehow, and this one we'll just align it since the year 1950. So this can be 0, 60s 10 years later, 20, 30, 40, and 50. Okay? So those are your L1 values. L2, we never change. We always enter it the way it says unless the problem tells us something specific to do, which is few and far between. Very, very seldom. So we're going to enter this into L1, enter this into L2. Now, the first question just says to examine a scatter plot and then to decide if a cubic model is appropriate. So you need to turn your plot 1 on, clean out any equations, and then zoom 9. Sim 9 will give you a scatter plot, and I'm going to try to sort of draw a rough picture of what it looks like here. That's pretty accurate on mine. Something like that anyway. Okay, so the first question simply says, would a cubic model be appropriate and why? So would a cubic model be appropriate? This is sort of one of those like leading questions. The answer must be yes because we're in the cubic model section, right? Seems reasonable. But we need to justify why. The answer is yes. Why is a cubic model appropriate for this? What do you see happen that none of our others have had?
Changing concavity.
Yeah, it changes concavity and direction, right? So we had one that changed concavity before. That was logistic. But we haven't ever had one that does both. This one changes concavity and direction. So this is appropriate because it changes concavity. And it changes, I'm going to say it's from increasing to decreasing to increasing. Because we sort of have this idea that it's probably going to look something like this, right? If I were to sort of connect the dots in a nice way on the Chili's menu with the connect the dot pictures of the children, right? You'd get something like that if it were smooth instead of it being bunches of line segments. So increasing to decreasing to increasing. So yeah, it seems appropriate that this is probably a cubic model. So we're going to give it a shot. The second question that you have says to find a cubic model. So we're going to do stat calc. Cubic model is number 6. It says cubic regression. Select number 6 and to put it in Y1 because you want to be able to graph it. This is a number of births, so I'm going to call it B of X. And if I graph it, it looks a lot like what I did with that red connecting curve over here, actually. Not perfect, but very similar to that. It does seem appropriate. And if I look at the model it gave me, I have a decimal point and then 269 if I round, x cubed minus 15. Notice it goes 5 and it has 3 9s and then a 2. Right, if I were to write these out, it looks, let me just write it here for just a second, don't copy that. I would erase my last, sorry, I missed a 5, my bad. 5 and then 3 9s and then a 2. If I left off the last 2, then that 9 that was listed there would actually push the other one to round up. So I'm actually going to get, come on. That this is going to have to be 6 with 0 0. Right? X squared plus 94.684 x plus 5378.032. Barely had enough space for that across the screen. All right, I've got a name and I've got an equation. I am not done. What comes next? The output. So what is the output in this model? Births. I need to say that. It's births. And we'll always say where the input, in this case I've used X, I always use X. So where X is. What is X? How did I do that? Yeah, it's years, and then I need to designate my starting spot, which I let that be 1950. So where X is years since 1950. And there's one more thing I need. What is it? An interval. So my lowest value that was on my L1 was 0, and my highest value was 50. So it's 0 less than or equal to X less than or equal to 50. Or if you want, you can actually use the words, and you can say for 1950 to 2000. It would be okay to use language for it too. It doesn't have to be an actual inequality. Okay, we have a couple of questions now that we're being asked, much like your problems in your homework do. So here's our cubic model, and we're being asked in part C to use that model to estimate the number of live births to women ages 45 and older in 1985, and then to do the same thing for the year 2015, and then to decide which answers sort of we're more convinced about. All right, so what would I do for the year 1985? We would plug in 35. And what would I do for the year 2015? Yeah, we would plug in 65. Okay, so we're going to do that. You can do that in your table, just the regular table, not the L1 table, the one that says you do second graph. You can plug in 35 and 65. So if I plug in 35, I have 1095.580. And 55, I have 19,369.785. Okay, but the outputs are actually what? What are these supposed to be representing? Births. So this first one, we'll just use regular rounding rules, is 1,096 births. The second one is 19,370 births. And which of those two answers is more convincing? We have more confidence in it being correct. Yeah, it's a 1985 one, and it's really not necessarily because 1096 seems more likely than 19,000. It's not why. Although it does seem more likely than the 19,000 given the data we had, right? Why should we be more convinced that that one's right when I look at the two values? Yeah, this one is more confident here in this one. And it's because it's in the data range. Or you could say because it's interpolation. The other one's extrapolation, right? So while it's true that we also probably are more convinced because, 1,096 kind of lines up with the data better than 19,000, that's really not why. We could just as likely have gotten a very believable answer for the year for 2015, and still we should not be as confident in it as the one for 1985. Okay? Any questions on that? Okay, one more question with this data. It wants to know, according to the model, in what year will the number of live births to women 45 and older exceed 10,000? So every now and then I will have somebody who will grab their calculator and they'll use their table and they'll just put in random years. And just keep putting in random years until they hit the number 10,000. It's not what we're looking for, okay? We're looking for a specific way of finding that concretely instead of guess and check. So I'm not saying that guess and checks altogether are bad. It's just not what we're looking for here. So what we are looking for is we're looking for those births to equal 10,000. Whoops. Okay, so this already is in Y1 in your calculator if you've gone through all the steps the way we've been working in class. And you're going to put this in Y2. So go down in Y2 and put the number 10,000. Now if you graph, it's probably not going to show up on your screen. You had that same graph that looked like my red curve right here, right? And that's all that you're still seeing on the screen right now. So we're going to just zoom out and see if we can see that line up higher at 10,000. So zoom 3 and just press enter. I see mine. Do you see yours? So when I zoom out of this particular graph, what I end up seeing is something like, let me draw an image, something like this. Here's my axis, and I have something that looks like this, and a line up here. Okay, so everybody see that particular kind of image. If you're not seeing that, now's the time to say something. Okay, Doran, let me come to take a look. Anyone else's calculator not looking like that? Okay, so Doran had a really good case on his calculator where he typoed something in his L1, L2 list, which happens. If you're looking at your data points and what you anticipated to happen, which was that it's supposed to be cubic, doesn't look like it fits well, it's a good thing to go back and check that and make sure that there's not a typo happening in there because it's easy to do. All right, so how do we find this place? We've done this several times in class now. How do we find that spot? Intersect. That's second trace, and it's option 5. This actually is only crossing one time. That's always nice when that happens because that means you can hit enter, enter, enter for first curve, second curve, and guess. And it will tell you at the bottom an X value. Let me do that back in white. And a Y value. So the X value, it says right here on mine, is 57.189. That's to 3 decimal places. And then the Y value, of course, should be 10,000 because that's what we put in. So it is. So what we actually just found is that this happens at X equals 57.189. And you have 2 options for what you could say to this. You ready? You can say 57.189 years after 1950. That's how your X input was determined. It's years after the year 1950. So that's correct, but this one actually asked you in what year. So what year would that be? 2007 is correct. So while the year is supposed to be the year 2007, and that should be your final answer, you have to show somewhere along the way that the value you got was 57.189. Does that make sense? Okay, so this is like maybe in, February, right? That's that 0.189 coming through or whatever. It's partway through the year. Okay, so that's cubic models. There's really not much different than what we've been doing with all of our other models, identifying, evaluating, finding where they're equal to a specific value and so forth. So we're going to switch gears slightly. The other part of this section is how to choose a good model. Because the reality is that somewhere along the way, if somebody asks you to model what their profit's going to be 6 months from now, they're not going to say in real life to you, use a quadratic model to find out what my profit will be in 6 months. Right? Of course not. You're going to have to look at the data and make a decision what model is appropriate based on the data you already have, based on what you expect to have happening, whether it's data trends or whether it's seasonal trends, right? Some things are seasonal, right? You don't sell near as many swimsuits in the winter as you do in the summer, right? Same thing for hot chocolate in reverse. My kids think they can drink hot chocolate any time of the year, but that's not really normal, okay? So as we're taking a look, there are a couple of very strong features we want to consider when we're making decisions on modeling. The first is to decide about concavity. This is step one. This is a really big important thing to make step one and not switch the steps. Examine the concavity. If your concavity changes, you only have two choices. Your choices are logistic. And if you'll remember, logistic looks like either this or this. That was terrible. How about that one? That's logistic. Looks like one of those shapes. Or you have our new one for this lesson, which is cubic. And cubic had 4 options of how it could look. It changes concavity. It could look like this, or like this, or it could actually have these sort of extreme sort of ups and downs in it. So if it changes concavity, and you've got a data set, and you aren't sure which one of these you could use, you could actually try logistic, and you could try cubic, and you could look at them and you could say, hey, look, the logistic model seems to just work better for my data. Or the cubic model just seems to match what's going on better. And you get to pick which one to use after that. If there is no change in concavity, then you have only one choice. I'm sorry, if there is no concavity, so I meant to say, if there is no concavity, you have only one choice. It's a linear model. And most of the time, you don't have to be told. You're going to look at it and you're going to be like, oh, look, it's a straight line. It's not very exciting, but you know immediately what it is. You will have no question. You'll know. It's the one concavity that always trips people up. Because when you have one concavity, number one, you have 3 choices. You have quadratic, you have exponential, and you have logarithmic. Not logistic, but logarithmic. Please understand, if you only see one concavity, you're not allowed to try cubic. You're not allowed to try logistic. You only get to use cubic and logistic if you see a change in concavity, right? So you are limited in what your options are for making choices. If it's quadratic, of course, it could look like a full parabola up or down, or it could even look just like part of a parabola up and down, right? That's quadratic. If it's exponential, it looks like one of those, and it's tapering off at the x-axis, always at the x-axis.
And that's always concave up, right?
It is always concave up, you're right. If it's logarithmic, it either looks like this, or it looks like this, and it has an asymptote at the y-axis. So it might even be good for me to sort of mark that on here so you can see that. There's my y-axis asymptote, and on the exponential there's that x-axis asymptote. Let me shift this down just a little bit. There we go. But they all, in those 3 cases, have one concavity. Okay, so once you've decided, let's say that you're doing one, it has one concavity, and you try the 3 options, and you're like, man, exponential and quadratic really both look good. Like, there's really nothing between the 2 of them that screams, you should use or you should use quadratic, or you should use exponential. So when that's the case, that is the only time, when that's the case, you do option number 2, or step number 2. You consider the end behavior of what's happening. With the context, like the problem that Mark asked about earlier on, that we were looking at, and we were talking about how it was leveling off, that computer ratio one, right? Like contextually, we don't expect it to go back up. That doesn't make sense for the context. Okay, so context and the end behavior is only considered after you have 2 equally good models. So if 2 equally good models both fit, then we will consider the end behavior. And that will lead us to decide what to do. So let's try that very fact. So we have a set of data. This table gives the average weight of the brain in a human as a percentage, human male, as a percentage of the body weight. Okay? So, right, the brain's not growing all that much. Your head size doesn't grow all that much as you grow up. Did you know that? It doesn't change a whole lot. So if you look like a little person, you know, like a 2-year-old, their head's vastly bigger to their body than yours is to your body right now. It's true. Okay, so obviously the brain's not changing in size that much because it doesn't have that much room to grow, all right? So taking a look at this one, you'll notice that we have a data set to plug in. So if you go into Stat Edit, you can plug these values in. There's no reason to change the numbers this time because I don't have any years present. So I'm going to put in exactly like it shows up. Okay, once you have your data in, go ahead and hit Zoom 9. That's the Zoom Stat button. All right, so step 1, examine concavity. There's 3 options. It either changes concavity, there's no concavity, or there's 1 concavity. What do your dot plot, your scatter plot, what does it suggest is happening? Tell me about concavity on your dots.
So it shows the concavity up.
Okay.
It could be exponential.
Whoa, slow down. I just want to know, Paula, because you're ahead of me actually. Do you see a change in concavity? Is there no concavity, or is there 1 concavity?
1 concavity.
Awesome. There is 1 concavity. So your dots, if they look like mine, should look something like this. Does it look like that on your screen? Fabulous. There's 1 concavity there. It's definitely not flat like a line, so it's not no concavity, and there's definitely not a change. Now, you kept going, so I'm going to keep letting you go, though, Paula, because you're doing exactly what you need to do. Tell me what about the concavity did you notice?
Well, for 1 concavity, which is always it's always concavity, up would be an exponential.
Okay, so you noticed it's concave up, okay? So it is concave up. Now you have to be careful because actually concave up happens in more than just exponentials. So definitely the exponentials concave up, right? Those are concave up graphs. And one of them resembles our data, right? This one right here, whoops. This one resembles our data. But logarithmic also has a concave up that sort of resembles our data, doesn't it? It's a possibility. And quadratic has an option that's concave up and resembles our data. So this is an example of one where you have to try 3 different models. So I'm going to walk you through that because it looks a little different than what we've done before. Let's just try quadratic first because it's the first one listed on my list here, okay? So I want you to go in and I want you to do a quadratic model. So stat calc number 5 for quadrag and put it in Y1. And let's graph it. And as you do, you might be kind of like, I mean, it's not too bad. It doesn't quite look as nice as I'd hoped, maybe, but, you know, it's tolerable. Do you get that feeling? Okay. I'd like for you to hit Y equals. Do you see on Y equals that the equals sign is like highlighted on your screen? If you press, like go back to it being on top of the equal sign and just press enter, you'll turn that off. Okay, I know this isn't projecting on my screen. I wish I had a document camera in here. We're still trying to find the document camera that disappeared from 304 when they swiped the room and turned it into a missions room. One day, we'll probably have it back. Okay, so right now, if you hit graph again, all you're going to see are your dots. Please try that for me. Just hit graph. Do you just see your dots? Awesome. Okay, go back into the regular screen. We're going to go to the second one, which is an exponential model. So you're going to do stat, calc, expreg, but you're not going to save it into Y1. You're going to save it into Y2. Okay? So vars, yvars function, choose number 2, Y2, calculate it, and press graph. Okay, compare those two. Which one was better? Does the exponential look like a better fit, or would the quadratic a better fit? You think? Neither one of them were great. Can we at least agree on that? I mean, they weren't a fabulous fit. I feel like that it's almost like flattening it out too much on the exponential picture, and there was more curvature with my quadratic picture. So let's just put it on hold right now. Hit y equals. You still have a y1 turned off. Now let's just turn the y2 off. Okay, and if you hit graph, again, you should just see your dots. And we're going to do it one more time. Exit your screen, stack calc, and we're looking for logarithmic, which is the LN reg. It's option 9. Don't put it in y1, don't put it in y2. Let's put it in y3. So what did you notice happened when you tried to put it in y3? Yeah. Why did it happen like that? Does anybody remember from when we talked about logarithmic functions? So consider. Yeah, it is, Lauren. So tell me what's wrong about that. Okay, you're right. Can somebody piggyback off of her idea then? What is wrong about having a 0 in the data set for a logarithmic model?
It's a fraction though, and so like.
It's like that. It's not a fraction, but it's like that. Martin? It doesn't exist. Okay, so undefined is I think what you're thinking of, and it doesn't exist is another phrase for the exact same thing. So it's undefined and it doesn't exist. What's happening? You have an asymptote. You're right. So on the y-axis, when y is equal, or when x is equal to 0, there's an asymptote for a logarithmic model, right? So I don't actually get to have a logarithmic option on this unless I were to manipulate somehow my data set. So this is no longer under sort of obligation. So we're going to say quit on that one. You don't need to calculate it. So if you go back in now and you want to look at these one at a time, if we look at y1 and we graph it, we're like, okay, well, I mean, it is what it is. And if we turn that one off and we graph it and we look at y2 and we graph it, we're like, well, again, it's not perfect. And 1 minute ago, we kind of said, like, we don't really think that this looks strongly in favor of one or the other. Does that make sense? Neither one's perfect. Both of them have some things about them that sort of look good and some things that don't look good. So when that happens, we have to consider option number 2, not option, but step number 2, which says that we need to decide what the end behavior suggests. So if I looked at a quadratic model, what will eventually happen if I continue out far enough to the right-hand side of this graph in a quadratic model? It'll go back up. Does that make sense? For the percentage of the body weight accounted for by the brain? Probably not, right? Do you know, I mean, unless you're like, what is it? What was the movie? The Curious Case of the guy that aged backwards. Do you know what I'm talking about? Benjamin Buttons, right? Like that happened to him, right? He shrunk up again. So if that were him, this would go back up. But life doesn't work like that in real life, right? Like that's Hollywood. So yeah, I mean, like it's not going back up. The percentage of your body weight accounted for by your brain is not going back up as you get infinitely larger and older, right? That doesn't work that way. Now, it's probably not also going to 0 like an exponential model, right? But it's still more realistic in the long term than it going back up. So, Mark, you said that you felt like the exponential was better. And while in terms of the data, they might both look sort of like maybe not ideal, it is better in the long term because the end behavior fits our context better. So when this one says that we want to choose the best fit model, the best fit model based on those two criterion, right? Concavity and then end behavior when I need to check it. It's an exponential function. So if you hit y equals, you can get that exponential function back out of y2. And let's see, this was the brain, so we'll call it b of x again since I'm dealing with my brain. I have 9.652 times 0.9, oh, it's 9295, so it's 930 to the x. What will my units say? Good. Percent of body weight. Accounted for by the brain. The next phrase is always the same. It says where x is. So what is x this case? Yeah, is the person's age. And I appreciate you saying in years. That is necessary. We don't always calculate age in years, especially if a child's young, right? You ask the mother of a young child how old they are, they don't tell you they're half a year old, right? They say things like 6 months, 8 months, right? So it's not always the same. So in years. What's the last thing I need? An interval. So what's my interval in this one? 0 to what? 16. It's always what I put an L1 in, okay? 0 to 16. Any questions on that one? All right.